Okay.
Yeah, hi, I'm Mihir and I'm from PsiQuantum. So we are a quantum computing company based in Palo Alto, and we are trying to build a quantum computer using photons as qubits. And at PsiQuantum, we have a large architecture team that from the beginning of the company has had a singular focus on achieving large-scale fault tolerance. And in this talk, I'm going to tell you about the general paradigm that we have found to be the best route to achieving this. We call this paradigm fusion-based quantum computation, or FBQC. And it's built out of only two primitives. It uses constant-sized entangled states, which we call resource states, and it uses destructive entangling measurements, which we call fusions. So these are the only two components that we use in our architecture. And both these primitives are actually available in linear optics, which is the physical platform being pursued by PsiQuantum. So in fusion-based quantum computation, we are getting fault tolerance that is tailored to operations that are natural for our physical system, which has a number of advantages in terms of the kind of physical noise that we see and in terms of ease of implementation. And here by constant size resource states, I mean that the size of these resource states is independent of the size of the computation. And typically, these resource states are of order 10 qubits. And both these primitives have, because of the fact that we are using operations that are natural for the hardware that we are implementing them in, both these primitives have high fidelity in linear optics. That is, these operations intrinsically have a very low probability of error. There are a number of other advantages of a photonic system. For instance, measurements can be performed on a picosecond time scale. Millions of components can be fully manufactured in a tier 1 foundry, which is important for large-scale fault tolerance. And easy networking allows for much less constrained geometries. But I'm not going to be focused on these advantages on this talk. This talk is going to be focused more on the general framework for fault tolerance. Some of you may know that entangling measurements in linear optics are probabilistic. For our purposes, all that means is that we can perform certain stabilizer measurements, but with a certain probability, some measurement outcome is erased, and this is called fusion failure. And one of the nice features of fusion-based quantum computing is that we deal with fusion failure within the fault tolerance framework, and so it's not a separate consideration. And although motivated by photonics, fusion-based quantum computing can be used in any physical system. And in fact, we believe it has certain properties that are advantages for other approaches as well. So I'll be describing it in very general terms. So the first primitive of FBQC, or fusion-based quantum computing, is constant-sized entangled resource states, entangled states that we call resource states. And in this talk, we'll be looking at stabilizer resource states, and we depict them as graph states of this form, where every node is a qubit and every edge represents bipartite entanglement. And so this is one particular example of a resource state that I'm showing you here. And this particular example has the form of a ring of 6 qubits. So in general, a larger resource state means more components in the path of a qubit in any physical system. And so small resource states are generally desirable. And in the case of photonics, bigger resource states imply more optical loss. And hence, keeping the resource states to be a small constant is actually essential for fault tolerance and for keeping the error rate low. The second primitive that we use is an entangling measurement that we call fusion, which is depicted by the orange oval here. So a very natural example of fusion is a Bell measurement that measures 2 qubits. So for instance, in this case, it measures these 2 qubits that is going into this particular fusion. And so it measures these 2 qubits and generates 2 classical bits, which are the XX and ZZ measurement outcomes for these 2 qubits. The focus of this talk is on fault tolerance. So we'll be considering situations where we don't always get these measurements perfectly. These measurement results can either be erased, that is, a measurement is not obtained at all, or the measurement result can be flipped, that is, we can get the wrong answer from the measurement. While looking at fault tolerance, we will look at a model where every measurement is erased with probability P erasure and is flipped with some probability P error. One thing I'd like to point out here is that these erasure and flip errors in this error model can arise because of something that went wrong with the resource state or with the fusion. And so we are essentially, through this error model, we are able to cover imperfections in both the primitives that we are using in FBQC. In particular, in a photonic quantum computer, our most dominant source of imperfection are photon loss and fusion failure. And both these imperfections can actually be mapped to erasure, which, as you might expect, because it's a heralded error, can be handled much better than other errors. And this is something that is extremely important for our architecture. So in order to perform our fault-tolerant computation, we arrange our resource states and fusions in a configuration, which we call a fusion network. So we'll have some arrangement of resource states. This is one example of some arrangement of resource states for which the resource state is still the same 6 ring. And we repeat it many times in this sort of unit cell. And we have some arrangement of fusions in this example. So for example, in this example, the orange ovals here are the fusions. And this arrangement of resource states, along with this arrangement of fusions, is what defines a fusion network. And in this particular example fusion network, we can numerically evaluate the performance of the fusion network, where every fusion measurement outcome is erased with probability P erasure and is flipped with probability P error. And I won't go to I'll go through the details later, but in this particular example, we find that this fusion network can tolerate up to 12% erasure and more than 1% error in every measurement of every fusion. And there's a large region here, which is the correctable region, which is the shaded region that you see in this plot here, where we can simultaneously tolerate both erasure and error in some amount in this fusion network. And so if you're in this correctable region, I can suppress the logical error rate exponentially by making the network larger. So these thresholds that I'm obtaining in this network are comparable to surface code. But most importantly, we can achieve this starting from small entangled states. So in a realistic physical implementation, you would expect the intrinsic error rate to be very low when you actually implement this. This is just one example that I showed you. It's useful to see this because it shows that within this FBQC framework, you can find a very simple architecture which performs at least as well as the standard surface code approach. But of course, within FBQC, there's a lot of flexibility in terms of using different arrangements of resource states and fusions, which can give you different fault-tolerant properties. So now I'm going to give you a few more details of the basic mathematical framework which underpins how you achieve this fault tolerance. It's all stabilizer-based fault tolerance, and I'm going to start with an even more toy example than the 6-ring example that I just showed you. The toy fusion network I'm going to describe is this, and it will make a bell pair with some fault tolerance. And this fusion network has 6 resource states that you see here, 1, 2, 3, 4, 5, 6. These resource states can be represented by a group, which we call the resource state group R, that is written up here. So the generators of this group are the union of this, are basically the stabilizers of all these resource states. And I've written up these stabilizers in a way that there's one column for every resource state. So for example, the stabilizers of the resource state composed of qubits 5 and 6 here is x5 z6 and x6 z5 that you see here, and similarly for all the other resource states. Now we consider that the fusions in the fusion network are the ones that you see in orange here. So these fusions can also be represented by a group which we call the fusion group F, where this group is generated by the measurements from all the fusions. So I have like one column for every measurement. So for instance, this fusion measures x6, x9, and z6, z9 on these two qubits 6 and 9, which is this particular column, and you have one column for every fusion that I have in my fusion network. As I had mentioned earlier, every fusion produces 2 measurements. So we have 2 generators from each fusion here. So the fault tolerance in FBQC arises from the fact that there is a redundancy between the resource state stabilizers and the fusion stabilizers. So there's some intersection between R and F. And so this can be represented by the check group C, which, as I said, is just the intersection of the resource state group R and the fusion group F. And if we write this group explicitly for this particular fusion network, in this case, we find that the check group has these 2 generators that you see here. So essentially what's happening here is that the fusion outcomes in a fusion network form a classical code, which is described by this check group. So individually, every measurement here has a random outcome. For example, x2, x5 could be either +1 or -1 when we go to measure this with equal probability in this network. But because these checks describe a classical code, the product of certain measurements must be +1 because the product of certain measurements here is defined by the resource state group. So for example, although x2 x5 gives a random outcome, the product of x2 x5, z6 z9, x10 x14, and z4 z13 in this example must be +1 in the absence of errors, because that's something that is defined by the resource state group. And if the product of these measurements gives us -1, we know that something is wrong with the measurements, with either the measurements or the stabilizers the resource state stabilizers are not exactly what we expected them to be. So we know that something is wrong with either the resource states or the fusions if we measure the product of these four measurements x2 x5 z6 z9 x10 x14 z4 z13 to be -1. So this loop around so this single loop actually gives me one particular check which is described here, and this loop here gives me another check which I've written up here. And these checks can actually be graphically represented in the form of a syndrome graph. Every node here represents a check. So this node comes from this particular check, and this node comes from this particular check. And every edge here represents a measurement from a fusion. So for instance, since this check had these four neighboring had these four measurements that constituted it, which you can see here. So this particular check in the syndrome graph has these four measurements, neighboring measurements. If the product of the measurements around the check is -1, we say that the syndrome lights up, and this information can be used by a decoder to determine the error class of a set of measurements. So for example, if we find that both these syndromes light up, then it's quite likely that this measurement, if both these syndromes light up, then it's quite likely that this measurement Z4, Z13 was the one that was erroneous. So the syndrome graphs actually, in general, in this particular classical code that you get from these checks, the syndrome graphs are actually not required to be connected. And in fact, in this case and in many other common examples, you'll find that there are two disconnected syndrome graphs, which we call the primal and dual syndrome graphs. But in this case, I'm just showing you one of them here. So these checks essentially allow us to find errors in the fusion network. In a full-fledged example, this is what would allow us to perform error correction. But in addition to correcting errors, a fusion network has to generate the long-range correlations that are needed for a computation. In this simple example, these correlations amount to us creating a bell pair between the unmeasured qubits 1 and 16. So how do I see what correlations I've developed in my fusion network? These correlations can actually be described by what we call the surviving stabilizers of the fusion network. And this is how you get the surviving stabilizers. So the original stabilizers of the resource state are described by the stabilizers R. Once I perform the fusions, only the resource state stabilizers that commute with F will actually survive as stabilizers of the network. And hence the surviving stabilizers are essentially, the surviving stabilizers are exactly the centralizer of F in R, which is what I've written up here. And when we write up the surviving stabilizers for this particular fusion network explicitly, you find that the surviving stabilizers include the checks. So we have C in the surviving stabilizers. So which is what you would expect, because elements of R that are inside F should commute with F. But in addition, this fusion network generates these two additional correlations, which are these two terms that you see here. And both these correlations have the following form. Both these correlations have some operator that acts on the unmeasured qubits 1 and 16. And there are some measurements in these correlations here. For instance, this particular term has this term Z4, Z13 that I've grayed out. So what this term, for instance, is telling me is that using this measurement X4, X13 that I'm getting from one of my fusions, this fusion network is giving me a correlation between X1 and X16 in my fusion network. And similarly, this term essentially tells me that using these set of measurements in my fusion network that I'm getting from my fusions, I get the correlation Z1, Z16 in my fusion network. And in other words, if we just look at these two, what we find is that using the measurements in the fusion network, we obtain the correlations X1, X16, Z1, and Z1, Z16 in this particular fusion network, which are the correlations that you would expect in a bell pair between 1 and 16. And that's basically what tells us that these measurements result in a bell pair between qubits 1 and 16 with some level of fault tolerance. So this was just a toy example. It illustrates how checks and surviving stabilizers emerge from a fusion network. But this is not a completely fault-tolerant fusion network because although I have some checks, not every measurement in this particular fusion network is part of a check. For example, I have a measurement, this measurement Z2, Z5, which I need to get this particular correlation, but it's not a part of any check in my fusion network. And therefore, a single error on this could mess up my logical correlation and give me a logical error in this particular fusion network. Furthermore, in general, for large-scale fault tolerance, we need a way in which we can increase the redundancy in the fusion network by making it larger to make the probability of logical error arbitrarily small. And so now we'll move and look at an example of a fusion network which has these properties and can be used for large-scale fault tolerance. And I've already shown you an example of a fusion network which can do this at the beginning of the talk. And that's the network composed of 6 rings that I showed you earlier. So in this particular fusion network, every XX and ZZ measurement from every fusion is actually a part of 2 checks. And so there is protection on every measurement that you have in this particular fusion network. And if you repeat the same analysis as in the toy example, you'll find that the syndrome graph has this structure. It's a cube with diagonals, and in this case you get primal and dual syndrome graphs which look the same. And in general, this is kind of important because that tells you that every measurement has, to some extent, has the same level of protection. And this syndrome graph structure allows us to use a regular decoder like minimum weight perfect matching or union find to actually decode. So above this stage, at a lower level, we are using different primitives. We might use different operations to get fault tolerance. But above this level, we can actually essentially use the same sort of fault tolerance structures that people are familiar with. So for people who have worked with syndrome graph in a surface code, a cubic syndrome graph structure would be familiar. And because in this fusion network, we are actually building up fault tolerance from these smaller resource states. We have this additional structure in the fusion network because of the way we are putting these small resource states together. We obtain additional structure in this syndrome graph, which is basically these diagonal edges. And in general, so this is just one example, but you obtain a different fusion network with different fault tolerance properties depending on which resource states you use and how you arrange them and how you actually decide to construct, how exactly you decide to get redundancy in your fusion network. If we look at the surviving stabilizers in this particular fusion network, they can be described by membranes which span across the logical qubit. And essentially, there are many membranes which span the logical qubit, which are topologically equivalent, which is essentially what gives us fault tolerance in this particular fusion network. So far, what I described to you was the fusion network in the bulk, which defines the fabric of the fusion network. This is the most important part of the fusion network because it determines what the fault tolerance threshold is. And by making the bulk larger and larger, I can get better fault tolerance properties. And I can suppress my errors further and further by making the bulk larger if I'm below threshold. But in order to perform gates, we need other features as well. And one such feature is a boundary. So this is what the bulk of the network looks like, what I just showed you. And in order to terminate the bulk at a boundary, we need to perform single qubit Z measurements. So I won't go into the details here, but by performing single qubit measurements on some qubits, for instance, by performing some single qubit measurements here, you can get a rough primal boundary. If it's in the middle of a unit cell, by performing some other set of single qubit measurements, you can get a smooth boundary. And by combining these rough and smooth boundaries, for instance, one could define an identity gate. I won't have time to go into details here, but we have an upcoming publication which goes into more details about how gates can be defined in this particular framework. So in photonics, you could make gates in the conventional manner as you see here, but there are a lot more opportunities because photons can be sent through fiber in many different ways. And photonics is not actually constrained in the same way as matter-based qubits. So this paper is going to talk a little bit about that freedom, and I'm here now. Also, I'm going to talk a little bit about how some of this freedom that photonics gives us can actually be used to actually be a little more creative with geometries and use non-locality slightly creatively. So what I described, so far I described fusion networks abstractly as resource states and fusions, but I didn't talk about what kind of devices can be used to build them. And naively, one might think that we need a device to create every resource state in the network and a device to perform every fusion in the network. But there are a number of games that can be played with space and time while constructing fusion networks. And so I'll describe some of these games now. So in the photonic setting, the physical component used to make a resource state is a photonic resource state generator. And this is a device which on every clock cycle, which in photonics can be really fast, let's say around 1 nanosecond, produces a resource state. So let's stick to the same 6-ring example. So every nanosecond, this resource state generator produces a 6-ring of this kind. So this is basically, this tells me how I get my resource states. And we also need physical components that can implement fusion. So fusion is a really easy operation for photonics that can be implemented with just 4 detectors. So I can take 2 resource states. Let's say these resource states are produced by 2 different resource state generators. And we send 2 of the qubits from these 2 different resource state generators through a fusion. And this is what I can call a space-like fusion, which is between 2 resource states generated by 2 different resource state generators at the same time. But I don't always need 2 resource states to come from 2 different resource state generators. I can also perform a fusion between 2 resource states created by the same resource state generator. So consider a situation where a resource state generator creates this resource state at time t equals to 0. And as soon as this resource state is created, the dark purple qubit here is sent through a delay of 1 clock cycle. In the next time step, the same resource state generator creates another resource state. And as soon as it is created, this blue qubit can undergo a fusion with this delayed qubit in purple from the previous time step. And this time-like fusion is showed in purple here. And so in this case, in this way, I can actually perform a fusion between 2 resource states created from the same resource state generator at 2 different times by delaying one of the qubits. So we can put these 2 elements together to create a fusion network. So consider a 3x3 layout of resource state generators. As you see here, it's a 3x3 generation of resource state generators. On every time step, these 9 resource state generators will create 9 resource states, as you see here. And as soon as these resource state generators are created, these space-like fusions between these resource states can be performed. So as soon as these are created, I can perform these orange fusions that you see here. And these are all space-like fusions because these are all resource states that have been created at the same time. And similarly, in the next time step, another 9 resource states are created and space-like fusions are performed immediately. And as soon as this second layer is created, similar to the example that I just showed you in the previous slide, in addition, we can perform these time-like fusions that I'm showing you in purple here between the layer at t equals to 0 and t equals to 1. So I'll use the same trick that I showed you previously. I'll delay this qubit and then perform a fusion with one of the qubits created on the next time step, which completes the 3rd dimension of our fusion network. And we can repeat this process to make the fusion network larger. So this is the same. So we repeat this process. We have t equals to 2, and we can keep going like this. And with just one delay, I've been able to make a fusion network. And this is the same 6-ring fusion network that I showed you a few slides ago. So you might have to squint a little to see that this is the same 6-ring fusion network, but it's actually the same network. And from this, it becomes clear that we don't need a separate physical device for every qubit in the network. And we can actually reuse a lot of the physical components in our fusion network. And so for instance, in this example, I only need devices corresponding to 2 of the dimensions of my fusion network. But I can push this game even further. So by using 3 delays, actually, by using just 3 delays, it's possible to create a full piece of the bulk using a single resource state generator, like a 3D printer, in the way that I'm just showing to you here. So the same resource state generator can piece by piece create a full bulk of the lattice and create a big piece of the logical qubit. And this is a similar trick to what was described in a previous talk by Kiana today. And we have a paper coming out soon which talks about how the flexibility offered by photonic qubits can be used in this way to make the bulk and also to perform logic more efficiently by using this inherent non-locality that photonics gives us.
We're starting to run into the question time now, so we're gonna have to wrap up quite quickly.
I just
okay.
So this is my
okay.
I'll just finish up. This is my last slide. So to summarize, fusion-based quantum computation is a framework for fault tolerance that is built out of hardware primitives that are natural for a photonic system. It is, however, a general framework for fault tolerance which has properties that would be useful for other physical systems as well. Every qubit goes through a very small constant number of components in its lifetime, which is important for keeping error rates low. And this is particularly useful in systems with high leakage. And the operations in the bulk of the computation don't depend on the gate that is being performed. And as a result, the logical feed-forward cycle can be much slower than the physical timescale, which relaxes requirements on the classical computing hardware, including the decoder. And finally, in addition to these general advantages, FBQC has several additional advantages for a photonic implementation. I had mentioned earlier that fusions in linear optic are probabilistic and there is fusion failure. In FBQC, the handling of the fusion failure is built into the framework. I didn't have time to go into the details, but even in the pedagogical example that I just showed you, even with this simple network, and even in the presence of fusion failure, the fusion network can tolerate more than 10% erasure due to loss in every fusion in the network. And in fact, you can design the scheme so that fusion failure hardly affects your loss tolerance. Having said that, there is a lot of flexibility for any hardware implementation. In this talk, I only went through a very specific example of a fusion network, which is based on the surface code. But the FBQC framework offers a lot of flexibility in terms of what kind of codes can be implemented, starting from different kinds of resource states and how primitives can be combined to perform logic more efficiently. So we have, this is actually our archive paper, which we put up recently. I can take any questions now.
Okay, thank you for a fascinating talk. So we've got quite a few questions on the Slack channel. Let me start with, so how does the resource state generator work? And what kind of fidelity do you think it can currently achieve? And I would probably answer that question with what success probability if the resource generator is a probabilistic device.
So what we normally do in these states is that so we have other papers coming out which will describe some of this, and this goes into more of the photonics. But so in general, the resource state generator, we have a whole scheme which is so the scheme to create the resource state itself is probabilistic, but we have switching networks that we've developed in the company which can actually give us resource states nearly deterministically with near deterministic probability. With extremely low overhead, and that's something that that there's a lot of work in the company on about how we use these switching networks to actually get these resource states. The way that you make these resource states is actually there are these linear optic circuits that can actually give you these resource states, and some operations while making these resource states are probabilistic, and that's why we use these fusion networks. Yeah, does that answer the question?
I guess the part of the question was what fidelity do you think that they'll be able to work at? So you said that with the switches you think they'll be near deterministic. So
they'll be near deterministic, and we've also we have parts of our architecture which can actually handle the fact that even if they're not deterministic, even if they don't arrive, we have ways to handle that in our architecture as well. That's probably the second part of the question.
Okay, there's a lot of questions, so I'm sure we'll have a lot of follow-up in the roundtable session at the end of the session.
Maybe on that question, maybe one more point I can say is that so there's two parts, right? One is that there's a deterministic fidelity, which is basically the resource state doesn't show up or something, and that's something that we can really handle very well in the architecture. And the second thing is that there can be a situation where there are Pauli errors, and that's or something in the resource state. So there are some the resource state stabilizers are not what we expect. So that's something we can handle as well in the architecture. But actually, those Pauli errors in a photonic implementation are actually much smaller. So that's one advantage that we have in photonic architecture.
Okay. I think we can just squeeze in one more quick question. Mike, have you got one that you picked out from Slack?
Yeah, could you just say a bit more about how the logical operations are implemented?
So I have a simple I have a simple example here that I don't know if people want to see. So basically, in general, a lot of Clifford operations can essentially be implemented using single qubit measurements. So for Clifford operations, we can define. So it's possible to define twists and defects using single qubit measurements. So for instance, in this particular example, I showed you how boundaries can be defined using single qubit Z measurements, which are oriented either along the unit cell or in the middle of a unit cell. So that allows us to implement Clifford operations. For non-Clifford operations, we still use magic state injection, and there are ways to do that, which are actually described in the paper that we have coming up. For magic state injection, there are a few more details which I won't have time to go into. But you can basically you can make one of the resource state qubits a sort of magic qubit, and you can do magic state injection that way.
Okay, well, there's a lot more questions, but we'll have to defer them now to the roundtable session. So hopefully you'll be able to join at the in half an hour's time after the next talk. Okay, that's all that. Virtually, thank you. And the next